This is example 13.3 from Discovering Design with Chemistry. A 250-gram sample of an unknown metal is heated to 350 degrees Celsius. It is then dropped into a calorimeter that contains 1,500 grams of water, which is initially at a temperature of 24.2 degrees Celsius. The water reaches a maximum temperature of 31.2 degrees Celsius. If the heat capacity of the calorimeter is 1410 joules per degree Celsius, what is the specific heat capacity of the metal? Let's label and then get started. So metal, I'm going to mark everything metal in red. So here's the mass of my metal. This is the temperature before we start the experiment. So it's the initial temperature. Again, it came from some other temperature when it's heated, but the experiment is starting when it's 350. So that's the initial temperature. And then we have some water. Let's move this up to 3. There we go. We have some temperature of some water and some grams of some water. So here's our water. Oh, I'm trying to make an M for mass. All right, there's the mass of our water. And then here is the initial temperature of our water. And then here is the final temperature of our water, so T of F, which, as we know, is the final temperature of everything. So we could label this with the color of the metal and then the color of the calorimeter if we want. All right. And then we're told the heat capacity of the calorimeter. So this is our big C. You can tell because the units are joules per degree Celsius, and our little c is joules per grams times degree Celsius, and then our big C is joules per degree Celsius. It accounts for, if it says heat capacity, it's the big C. If it says specific heat capacity, it's the little c, and we have to take into account the mass when we're figuring it out. All right, this is a messy looking thing. Let me clear that up. All right, so big C is this one. And what we want to know is what is the specific heat capacity, so little c, of the metal. And I'll put it in red so that we can remember which one it is. All right, so what do we have? What do we need? We want the little c for the metal. So we're going to use this equation, and we want this one. And we have the mass of the metal. Do we have the change in temperature? We can get it using our initial and final. And this is the thing that we want. So what we don't have is the Q. If we had the Q, we could plug in a number for Q, M, change in T, and then, or change in temp, and then we would be able to get the C. So we need to use other things, the water, for example, and the calorimeter to find what their Qs are. Do we have enough to find their Qs? For the water, we need those same things. We need mass. We have the mass of the water. C, we have memorized the specific heat capacity of water. I should add that to my list of equations over here. The little purple boxes I put up to help us remember stuff. And then change of the T. So we have everything we need to find Q for the water. How about the calorimeter? They gave us a heat capacity for that, so it means we can't ignore the Q for the water. Because the calorimeter, we don't need to, because they gave us the heat capacity, it means its mass was already taken into account. So all we need, we'll be using this equation. I should probably change a different color. We'll be using this equation for the calorimeter because we have a big C. Do we have the change in T for the calorimeter? Yes, because the water is in the calorimeter. So whatever the change in T is for the water, it's going to be the same change in T for the calorimeter. So let's get started on the water and the calorimeter, find their Qs, and then we can use this bottom equation right here to find the Q of the actual object, and that will allow us to have the last thing we need for the second equation over there that we're going to use to find the specific heat capacity of the metal. So that's our plan. So in case having a plan helps you, we're going to find the Q of the water and the Q of the calorimeter, I'm not writing that whole name, and then use those to find Q of the metal thing. And then we're going to use that to find the specific heat capacity for the thing. Let me also go ahead and list that the specific heat capacity for water is 4.184 joules per grams time. There we go. All right, so when we get to that step, we'll have it listed already. All right, so first step, let's find the Q for the calorimeter. So I'm going to put Q and then like a little CAL like a subscript so I can remember which Q I'm finding. I'm also using colors, but on your paper you may be using a pencil for everything, so use subscripts to help you keep track of what is what. So for this one we need big C times change in T. Let's come over here real quick and find change of T. This applies to the calorimeter, but it will also apply to the water. So we need final minus initial. So that is, final is 31.2, and the initial is going to be the same as the initial water, 24.2. This is why I like to label everything. It makes it so much easier to find when I'm trying to work with stuff. All right, so that's 7.0 degrees Celsius. Just because they're both 0.2, don't accidentally drop that 0. Your calculator will probably just tell you 7 if you type those two in, or if you did it in your head, you might just be like, oh, 31 minus 24, 7. But remember, we have to keep precision with significant figures. So since they're both to the 10th place, when we subtract them, the answer is to the 10th place. And that is also our change in temperature for our water. So we're going to keep that in mind. All right, so now we can plug stuff in. They told us 1410 joules per degree Celsius. And then we just found our change in temperature. That's 7.0 degrees Celsius. Our units will cancel. And I'm trying to decide if I want to go beside it or under it. I think I can squeeze it in. All right, so when we multiply these two numbers, 1410 times 7, we get 9870, but we cannot keep that whole number because 7.0 only had two significant figures, so we can only keep the first two. So we need to use that 7 to round it up. So that's going to be 9900. So 9900, and that's in joules. All right, now let's find the Q for our water, because that was the next step in our plan. So the Q for our water, MCAT. All right, so our water mass is 1500.0 grams. Our water specific heat capacity, you know what it is, 4.184. And then the last thing is our change in temperature, which is the same as it was in the other one. So we're going to multiply all of those, and I'm going to just keep going like that. Okay, so before we look, we have 5, 4, and 2 significant figures. So that means we get to keep 2 once we do this problem. So 1500 times 4 times 7. Again, I know it's 7.0, but my calculator won't care. All right, so 2 means I only keep these first 2, and I'm going to round. So that'll be 44,000 joules. So 44,000 joules. All right, so there's the Q of the calorimeter and the Q of the water. So now I can find the Q of the metal, because remember, the Q of the object, put a negative in front of that and put the other Q's being added over here. I probably should actually do those in their matching colors. How about I just underline them? So Q of the water, Q of the calorimeter, and that will give me the Q of my metal. So, and then I'll have to flip the sign because this has a negative out in front. All right, so the Q of the water was 44,000 joules and 9,900 joules. And I'm adding these together. That's going to give me negative Q of the metal. Now, because I'm adding, this one goes to the thousands place, this one goes to the hundreds place, so I can only go to the thousands place when I add these. All right, so 44,000 plus 900. So I can only go to 54,000 because I have to keep the thousands place as my most precise thing. So, and because that equals negative Q of the metal, I'm just going to go ahead and say Q of the metal is negative of this number. So Q metal equals negative 54,000 joules. All right. So now that we have our Q, we have all the pieces we need. I'm going to go ahead and find the change in temperature for our metal, but if you didn't think to do that and you jumped right into plugging everything in, then when you got to this step and realized, oh, I need to plug in change T, you could pause, go to the side, find it, and come plug it back in. I'm also going to rearrange. I'm putting M here for metal. All right, so the final temperature of the metal is the same as the final temperature of everything else involved in this experiment. The initial temperature is 350.0 degrees Celsius. Again, I'm dropping my T there. All right, so final temperature, and I probably should put metal here in case I wasn't color-coded writing so you could see. So I'm going to subtract those numbers, and right, so 31.2 minus 350, so I get negative 318.8. So that's the change in T. Now, before I start working this problem, I want to rearrange this equation because I'm solving for the C. I want the specific heat capacity, and so I want the C by itself. We've done this a few times in previous problems, so I'm just going to go ahead and write it. So C equals Q of the metal. I'm not going to write the word metal. This whole thing's in red. You know I'm doing the metal. Over M, change in temp. All right, so little c equals the Q of my metal, which is negative 54,000 joules. That came from here, divided by the mass of the metal, which is up here. So 250.0 grams. And that's multiplied on the bottom by the change in temperature, which is over here. Let me put my units back, which is negative 318.8 degrees Celsius. Now, when I do all of this, I'm going to get the units that I expect to get. Nothing cancels out, but that's the unit I expect to get for a specific heat capacity. And I can only keep two significant figures because of the 54,000 on top. And these two numbers are going to cancel. Let me make that cleaner. And so I'm going to end up with a positive answer. So I'm not going to put any negatives into the calculator because I can see that the answer is going to be positive. I'm just going to let the calculator do the number work for me, but not the obvious stuff. Times 318.8. That's what's in parentheses, and then that's my final answer. All right, so two significant figures means I only get to keep these two. The 7 after that rounds it up to 0.68, so 0.68. So that's my final answer. I had to do a lot of steps to get through this, but you can see that if you think through, the first step I do when I have a problem like this, there's a lot of numbers and a lot of things, is I start labeling everything. Sometimes, like in this case, I label it on the problem because I have a colored thing, but you can also label it out to the side if you realize you have a bunch of stuff. I'm going to slide this to the side so you can see what I mean. If I'm writing on my paper and all I have is just my one boring colored pencil, as I'm starting to read this, I make a plan. I'm like, all right, I have a metal. I have the mass of the metal, and I'll label what it is. And then they give me a temperature for the metal. And then they tell me about a calorimeter with water, so I make a new column. I'm like, okay, water. And they give me a mass for water. And I try to line up the things that are the same on the same row. And then they give me the initial temperature of the water. That's convenient that they gave them to me in the same order. And then it tells me the final temperature of the water, which is 31 point. I'm getting kind of messy over here with my writing, but I just want you to see another way to write it, because I know that's also the final temperature of the metal. I go ahead and write that down. And I can even go ahead and put change in T equals so that you could see that I've left a space open for that to be written. And then it tells me about the heat capacity of the calorimeter. And so I'd make another column and say calorimeter. And because it was because it wasn't a specific heat capacity, but a big one, I don't need mass, so I would just ignore that. I could probably say something like same. Actually, all that would be the same. And then I would put the number here. So I would have that. That's a messy J, sorry. And then I would, when it asked was the specific heat capacity of the metal, I would say C equals. And then I could keep track of my information that way too. And I could see, all right, I want this. Look at all the equations that I know, all the formulas that I know, which one has a little c in it. Okay, it's that one over there, the one the red arrow is pointing to. What else do I need? I need mass. I need Q, so I might put a Q down here. I need change in T. I've already labeled a space for that. And then I would think, okay, well, I can't find the Q or the C using what I've got. What else can I do? And then you can realize, wait, I know the C for water, the little c. I can find the Q for this. I can find the Q for this. I can use that bottom equation to use these two that I can find and find this one, and then that gives me the pieces. So as you're working these problems, start by just labeling what you have and what you know, and then look at your formulas and see how can I get from here to there, and use this where I put these little scratchies. Instead of writing that, I would write a plan of what I'm going to do over to the side. That way, when you go to work the problem, you can stay focused, because it's really easy to get to the end of something and say, okay, Q of water is 44,000 joules. That's my answer, when that is not even what they're asking for. But when in multi-step problems, it's really easy to get lost in what your final goal is. And so having a plan written somewhere to the side, even if it's just like a find Q of this, find Q of this, find Q of this, find C of this. Like, even if it's just that process, it gives you something to look at, so you don't get distracted and answer too early with something that's not what they're asking for.